the pre-program. Welcome, everyone. I'm Patrick Murphy. I'm one of the co-chairs of the BSA Committee on the Environment, along with Michael Grant. We're excited to share this presentation with you, but before we get started, a couple of points. The first, we want to let you all know about a session next month, which will be on April 21st. Same, Wednesday, 6 o'clock time frame, like we have right now. And next month's topic will be decarbonizing campus. So that colleges and universities were among the first to make commitments to be net zero. And over the last 10 or 15 years, they've made great strides in addressing what I'd call the lower hanging fruit. But now they're running into the more challenging, era of moving towards net zero, specifically around their central heating plants, their central energy plants. So I'm excited, to kind of bring my engineering role to the Committee on the Environment to introduce to you a number of facility managers and capital planning experts from a couple of colleges to speak to how they are addressing this big challenge that they have to decarbonize. So we're going to have representatives from Dartmouth College, Abby Bjorklund, Amherst College, Jim Brassard, Colby College, Mina Admonson, and possibly one other. And they'll share with you the work that they're doing, the master planning they're doing, the implications for us as a design community working on those campuses, and how they are planning to get to net zero in the next 20 to 30 years. So stay tuned for that. You'll see, you'll be able to sign up on the website, the BSA website soon. And with that, I will hand it over to my co-chair, Michael.
Hello, welcome to the COTE session. I wanted to mention before we jump in that the BSA Committee on the Environment is currently in the process of engaging the next co-chairs for the Committee on the Environment. And by tradition, what the Committee on the Environment has done is solicited statements of interest, and you can send those to Susan Green at the BSA, and you can take a look at previous statements of interest from myself and other co-chairs on the website if you want to get a look at that. And it'll also give you a little sense of what's involved in the position. And then in June, when we meet for our monthly session, we're going to hold a vote by the attendees of that session, and that's how we're going to pick the next two co-chairs. So think about it, and we hope to get a lot of interest and see the candidates in June. So turning to tonight's session, we've got Opal Architects, and we've got the partners of Opal Architects, Matt O'Malia and Timothy Locke. Thank you guys for coming to talk to us about zero carbon and all wood buildings. I want to just mention before you start that Opal Architects is a fascinating firm that was founded back in 2005 in Belfast, Maine, and it was founded as part of a design build concept. It was half of a design build firm, but has grown into an architectural practice in its own right that is innovative in many different ways, part of which is that it's involved in manufacture, and I hope the partners will speak about that a little bit, but also that for all of their projects, they're committed to the Passive House standard. And I don't know of any other firm who is committed to that, even though it is becoming more and more common. So we're just thrilled to have them here to talk tonight, and also just to learn a little bit about the innovative practice that they've built over the years. So with that, I'm going to turn it over to Matthew and Timothy.
Thank you for that introduction, and thank you for having us tonight. We're really happy to be able to talk about the work that we're doing in a couple different areas. I think for us, as you point out in our kind of firm history, sustainability and performance is kind of fundamental and critical to how we view the practice of architecture and the role that we're playing. And we're going to try and hopefully kind of spell out why we feel that way, what our priorities are and what they're driven by. But also how we put those concepts and ideas into practice in the work that we do. Just before we get into it though, I want to do introduction for Tim and I. So I'm executive partner and I was the original co-founder of Geologic, which is the design build company that was alluded to. And in the meantime, Opal was launched in about 2018 as a full architecture firm, and at that point I took on Tim Locke and Riley Pratt as the partners, which is kind of where Opal comes from if you look at the initials and the name. And we're focused on a diverse practice, working kind of all over New England and the Midwest right now on a variety of different building typologies. So Tim, if you would want to jump in real quick.
Sure. I'm Tim, as Matt said. I'm the management partner at Opal and specialize largely in institutional projects at scale, passive house at scale, advanced building performance at scale, total carbon at scale. We'll talk about all of it tonight. It'll be fun.
Great. So just to give you a little bit of background with the firm, it was launched as a design build, and I think it's important to kind of give you a little bit of history of how we got to where we are, what we're going to tell you tonight. Our focus was passive house from day one. When we started the first prototype project, we focused on the passive house standard, and it was very, very new technology in that day. And we ended up certifying the first passive house main, and it was the 12th passive house in the entire United States. So very early days, very cowboy, a lot of sort of making up the details as you went, importing ideas selectively from Europe and so forth. My background, I have a degree in architecture from a German university. I speak German. So for me, the idea of using a German energy standard was kind of familiar. We imported our own windows directly as there weren't too many options in the day. And so we kind of built a practice, design build practice, or a lot around innovation and having the opportunity as a design build to have this feedback loop from the design concepts to construction and back and forth, which allowed us to innovate rather quickly on a number of projects. And I think gave us a lot of experience right off the bat with passive house technology that allowed us to scale that. We ended up building quite a few projects around the Midwest and New England, and worked with some interesting institutions along the way, certifying the first laboratory with the University of Chicago and Residence Hall and here in Maine, and some other similar kind of groundbreaking passive house projects. But one of the things, as we got better at building passive house, that became more and more important and critical to us, and it was driven by two things. One was we were design build, so we had direct feedback from our crews that were building these buildings. And two, we started looking at life cycle analysis and carbon footprint and modeling in addition to our energy models. And we realized building passive houses was great to reduce operational carbon. It was the obvious choice in terms of a building solution that was appropriate for the future. But the means to doing that, we had more and more issues with, because ultimately a passive house, one of the main differences between that and code compliant construction is the fact that you're using 3 times the amount of insulation. And so insulation became a very important topic for us as we started the life cycle analysis. We realized that the existing mass market consisted of foam and fiberglass, which are all non-renewable, toxic, non-recyclable materials, primarily created from fossil fuels or had high embodied footprints, energy footprints and carbon footprints, and we're completely at odds with the passive house standard and the values around sustainability that we have as a practice. That drove us to look a little further about different options. We went to Europe and discovered wood fiber insulation as an alternative, and we started to utilize that in conjunction with a much more robust life cycle analysis modeling and looking at the sort of full carbon, not just looking at operational, once you occupy the building and how does it perform going forward, but looking at all the inputs in the construction process and understanding those and optimizing those. Because what we realize to get to the zero carbon future that we feel is so critical in architecture is that we could no longer ignore the embodied carbon, the carbon footprint of the materials that we were building. So that really caused us to take another kind of, I would say, revolutionary turn in our practice, where energy modeling has always been fundamental to what we've been doing, but then we brought in life cycle analysis, the same sort of discipline that we use there to optimize the carbon footprint of the building as well, or minimize that, you might say. So what we're going to talk about today about is that process and where that has led us and how we're implementing that in projects, both in small scale and large scale. And as well, I'm going to talk a little bit about Timber HP, which is the offshoot, a sister company from Opal, which is going to be manufacturing wood fiber insulation here in Maine. So I'll tell you just a little bit about that and why we're doing this crazy large project, why we are actually undertaking that. So I'm going to try and change the slide here. So as I said, what we're going to be doing is just talking a little bit about buildings, the role of emissions and the carbon footprint in buildings, some of the products that we see as opportunities to manage that, and then get into some case studies. I think this slide right here, as architects, we're all pretty aware of, and that's the 40% of the carbon emissions worldwide is accounted for by buildings. And when you break that down, it's a 1/3, 2/3 relationship of building materials and building operations. When we started with this position, we thought, okay, operations is clearly the problem. Passive house is an excellent solution. Let's implement that. We're doing everything we need to do. We're doing everything we can do. But the reality is that is just a sort of snapshot in time about the impact of buildings. Because what's important to keep in mind is we're on a continuum here of population growth and expanding demand and requirements for additional buildings. And if we think of the scale of buildings and construction over time, while it is absolutely critical to ensure that every new building built is to the highest energy efficiency standards we can possibly build it, the more and more buildings we build, the larger and larger impact on carbon and the atmospheric carbon we're going to have because of the carbon required to build these buildings in the first place. And when you look at that over time, and when you also look at the impact of regulations, increasing code awareness, and the drive towards higher efficiency, you realize actually that going from 2020 to 2050, that according to the AIA and corroborated by many others, is that operational carbon, cumulative operational carbon will be reduced because of energy retrofit, increased insulation, and renewable energy systems, which is going to flatline our operational carbon over time. But what does not flatline, which will continue to increase, is the carbon required to build buildings in the future. And so when as a passive house practitioner, I say, okay, the impact of doing the right thing with passive house or high performance building will be seen, and collectively, from my perspective, starting in 2008, when absolutely nobody heard of passive house, to today, where there's millions of square feet of passive house being built at different types of projects and different types of scales. To me, the change is phenomenal and fundamental. While it's still a small percentage of the total square footage being built in the United States, passive house is having a massive impact on the overall mindset and trajectory of buildings. But the same thing needs to happen with our building materials. And if it doesn't happen, we're going to solve one problem and still remain having a really large carbon problem with our building material selection. So one of the things, as I said before, we looked at was, as passive house practitioners, one of the differentiators that we could control was the insulation products we use, and the fact that these are totally not sustainable options. In addition to being non-renewable, non-recyclable, in many cases toxic, they also have high carbon footprint, and based on the material, the carbon footprint or the global warming potential is extremely high. So as we were looking to solutions to have sort of a positive carbon future, we realized that in addition to some of the other construction systems we'd be using, most notably CLT, insulation is also a big area that we should focus on. And that's when we started down the road of understanding and developing wood fiber insulation. Wood fiber insulation has an established track record in Europe, 25 years. It's the largest, fastest growing segment in the market there. And what's interesting is when you look at the forest reserves in Europe to create wood fiber insulation, it's actually quite small relative to the United States and Canada. As a result, our wood costs are a third the cost they are in Europe. So whereas wood fiber is a premium product in Europe, it for us will be a cost competitive product. If you're not familiar with it, there's 3 products. There's the blown-in replacement for cellulose, there's the bat, which is press fit replacement for mineral wool, and a board product. Based on our early testing, the bat and blown-in have a Class A flame spread rating due to the borate in it, so it's appropriate for all construction types. The board has a Class B, so primarily more residential. But as you'll see in the project Tim presents today, that we've done a large institutional project with the board. And I think, again, one of the key characteristics of wood fiber insulation is it's vapor permeable. Foam, when required as a continuous insulation, is completely vapor impermeable and presents a liability of condensation and forming a dew point at the insulation, at the sheathing layer, whereas wood fiber insulation is like Gore-Tex. It's breathable, windproof, and allows moisture to move through the assembly as a vapor open assembly. The other big differentiator is that it is carbon storing. Trees, as we know, sequester carbon through their growth cycle. At the end of life, they can either get cut down and decompose and release the carbon, or we can store it in building products. And that, I think, is the big differentiator from standard insulation products, because when you look at the life cycle analysis going through that, while we do require energy to make wood fiber insulation comparatively, it starts with this negative carbon balance, or this stored carbon balance that the other insulations don't have. So when you're looking at the life cycle, starting with carbon, the A1, the carbon, stored carbon, and then when you look at extraction, transportation, and manufacture of these materials, obviously there's these increase of carbon footprint, as does wood fiber insulation. But the key with wood fiber insulation is that we have that negative carbon balance, which means that when we build wood fiber insulation, it comes to the job site with a negative carbon balance, where all other insulation materials come with a positive carbon balance. Like CLT, the key to a wood fiber insulation is it's a replacement for high carbon footprint materials. So, and that's the big differentiator, because for existing insulations, mass market insulations, because of their carbon footprint, it takes about 7 to 8 years of operational carbon savings to pay back the original carbon footprint of these materials. Whereas wood fiber insulation comes carbon negative to the job site. And I think the reality is, when we're thinking about retrofit programs, which are there to save carbon, there to reduce the energy demands of buildings, to think that by installing conventional insulation, it takes 8 to 10 years to realize, to first of all neutralize their carbon footprint and then realize the benefit. Given the sort of rate of climate change, it's really not a good balance. We need to look at materials which are, first of all, carbon neutral or carbon negative in offsetting, and wood fiber is one of them. When we produce this in Maine, we're going to use 90% FSC certified. We're using a waste stream from the lumber industry, so we're not clear cutting trees to make this product. We're using the offcuts and the residuals from the lumber industry, which means basically we're taking the round logs, cutting them into boards, and all the pieces that weren't becoming the boards are going to be created into wood chips, as you can see here. We refine them into the wood fiber, add adhesives, press them, and then have, well, the 3 product line, which is the board, bat, and the loose fill. So in all, a very low energy intensive process, which therefore obviously maximizes the stored carbon in each of the products. Timber HP, GoLab is a startup, and part of what we've done is we've purchased manufacturing equipment from a used plant in Germany, and we just had shipped to the US. It's just arrived in Searsport, Maine. We also bought this massive 200,000 square foot manufacturing facility, which was the former UPM paper manufacturing facility in Madison, Maine. It used to be called the New York Times paper mill because they used to produce the Sunday section of the New York Times there. Like so many paper mills in Maine, we've lost 6 since 2016, which has had a net negative impact, financial impact on the state of $1.6 billion annually. So what we've done is we bought this wonderful facility built in 1980. We're going to be installing this new value-add processing equipment for this new product, revitalizing the mill, bringing jobs to Madison, Maine to the tune of 113 new jobs, and really sort of providing a value-add stream for the Maine forest products industry, which is hurting, to say the least, because of the decline of the paper industry. So I think this is one of these interesting cases where the synergy between new environmental carbon sequestering high performance product, which is cost competitive with the standard insulation products out there, is the catalyst for economic regeneration in Maine and rural communities, which is so important, particularly in a state like Maine, where we've been so devastated by that, as well as being a highly sustainable environmental solution. So there's really this sort of incredible triple bottom line opportunity. We're going to be getting up into production in 2022. So if anyone wants to have a look at a massive paper mill, come on up and visit us. I'm going to move briefly on to a project that we recently built, which is this sort of prototyping of all wood construction, which was a project in Lake Warromog, Connecticut. It was a CLT wood fiber construction. It was a funny little lake house. It was a pre-existing condition in the shoreland zone. So it was an existing non-conforming. And so we had this very tight little cottage shape that we could build within. So the form of this building was completely dictated by the pre-existing structure that we could not expand from. And so we inherited this funny little cottage form. But the thing that we said that we wanted to experiment was the idea that what happens if we take a really complicated form like this and use the CNC cutting of CLT, the precision of that, to make this really complicated shape. Most people assume CLT should be used for multifamily, this sort of lining the various, regular structural systems. And we said, what if we don't do that? What if we use the export from our computer model into production as the catalyst for using CLT? So managing the complexity of that building form. And that's exactly what we did. So we took this 1,500 square foot plan, built to the Passive House standards, triple glazed windows, high performance exterior wood fiber insulation throughout. Very simple program, basically 2 bedrooms plan. We created a computer model of it, which we worked with KLH, which is an Austrian CLT manufacturer, and we had them create, as their process is, very, very detailed CNC or computer model of the CLT. And as you can see here, there's a lot of options the way you can structure CLT. So there's a lot of control in the process of design. So we worked with them to do that. They produced this incredibly accurate model that we had the opportunity to put together very quickly on this very tight site. I don't know if this video is going to play or not. Here we go. I'll explain a little bit. So this is just a little video showing how we installed this CLT project. As you can see, all the elements are pre-cut, very fussy construction. And it was like 4 days in November, windy, nasty, rainy. So if you can build a building in 4 days in that condition, you can build a building on pretty much anywhere. So, but what was really important to us as a proof of concept is that the level of precision of the CLT, the dimensional stability, and the accuracy of the cutting was something that was really a great way to leverage in construction going forward in order to control or reduce labor costs. So while it's totally appropriate for multifamily and large scale buildings because of fire resistivity, it's also really appropriate for smaller scale structures because of its exact precision and ability to increase the efficiency of the schedule of construction. So again, some of the shots are on the CLT there as well. In terms of the detailing, there, as you can see, there's a wood fiber shell. It was actually quite complicated with inboard gutters and a lot of very fancy detailing. Here's an image of the wood fiber insulation being installed. As you can see, we ran downspouts, another sort of layer of infrastructure within that behind the facade system. The roofing system was actually a Tesla roof, which we liked a lot because, as you saw from the form, it was very complicated. There wasn't a large south-facing exposure where we could do a lot of south-facing solar collection, but with the having solar panels on every surface of the building, we have a much greater ability to have combined total collection. As you can see in this graph below, if you look at just south, we weren't really going to maximize and have sufficient impact on energy production. But when you took south, east, west, and north, we really got to the point where we were having the energy outputs to make the building net zero. And just to run through that, what do the numbers look like? Again, we're trying to go for this negative carbon building, both operations, but also embodied from construction. So looking at what we did, 22 tons across laminated timber, 18 tons of wood fiber, and 10 tons of other wood. A lot of people default to the other wood because that's easy and available, but these guys, the cross-laminated timber and wood fiber insulation is really where you find your gains, as you can see in this slide. So when you look at the stored carbon or the carbon negative footprint of these buildings arriving to site, you can see the relative impact. So CLT is always the big winner, given the mass, the density, and the scale, but wood fiber doesn't do so bad itself. And again, those two, in this case, CLT isn't replacing concrete structure or steel, so you don't have that offset. It's residential, so it's replacing wood, but obviously when you're talking about steel structures going to CLT, you have that offset. When we look at the carbon footprint of the other building materials combined, we're going to look at the offset of the carbons to come out with positive 23 tons of CO2 per year, which obviously isn't carbon negative to begin with. We're trying to figure out how we do that. We haven't gotten there yet. But alas, we do believe that it's important to take into consideration on-site renewable energy production as a way to reach those goals. And therefore, using the Tesla roof, when you look at the embodied and operational carbon combined, or global warming potential combined, as you can see, obviously embodied global warming potential is a constant. You start with that amount of carbon, you stay with it, but the operational is cumulative. But then when you're offset with our productions, we're carbon neutral for the entire building at around year 7, and we go into negatives by year 10. And every year forward, we will have a positive impact on carbon by having built this building. So I think that's what we really see as the opportunity. And I don't think architects have really thought of it in those terms, but in building a building, we can have the opportunity, we can have the impact of actually reducing atmospheric carbon because we built that building. And that's what I think we're proposing here, is thinking of it differently, that not accepting that every building has some amount of environmental negative impact, but to think with the right kind of construction materials and on-site renewable production, that every building we build can actually be a force of positive change in the environment going forward. And for us, that's what we founded Opal on, is that belief. And we're trying to put that into practice with every project going forward. So what I'm going to do now is hand it over to Tim, which is going to take just a second here, and he'll talk about how that works and plays out on larger scale projects that we've designed recently. If there's any questions while we change it up here, I'm happy to answer anything.
Thanks, Matt. I am going to just make sure my screen is sharing okay. I'm assuming everybody can see that. Get a thumbs up. All right, thanks. So, you know, I think that when we take that out to the entire practice that all of us in this discipline are engaged in, it's always important, to me at least, when we approach problems, to consider our role. And if we think about having, as Matt said, this one earth of resources, yet on average across the globe, we're using 1.7 Earth's worth of resources. And if we prorate it for the US, we're actually using 4 Earth's worth of resources prorated for our population. All of a sudden, all of those choices, whether it's building materials, whether it's energy, whether it's other ecological impacts, have this huge, huge and important role to play. And as architects, we are makers, right? And this quote I just love so much, that the ultimate hidden truth of the world is that it's something that we make and could just as easily be made differently. And I think for our discipline, it's really something that is a driving force behind the way I think about architecture, the way I think about our work, and the way to think about what that future could possibly hold. And to Matt's point that he just made at the end, what if buildings improved our world? What if we didn't automatically think of that research draw as a negative impact on climate, but the potential it could have to be a contributing factor towards a positive future? And that really is core to our mission. We try to take it to all projects, and that doesn't just stop at energy and materials. And of course, as Matt said, one of the core pieces of that is Passive House. And so I'm going to start with a project that's actually down in your area. This is in Beverly, Massachusetts, for the Waring School. And this is a project we're just finishing up right now. It's actually got 2 weeks left. They're rushing to completion. And we call this project the Bridge. And to us, it's about Passive House, taking on that challenge of Passive House holistically. And Michael had made the point at the beginning that we do really do this, that we are a firm that has decided that Passive House is a baseline of entry for our projects. We have some adaptive reuse projects where that's not a core component, but 95% of the projects in our office, if they're new construction, we're starting with Passive House as a baseline, and we're drawing that thick wall because we are thinking about that relationship to those resources actively. And so that means taking on really challenging projects sometimes, because if you say everything can be a Passive House, then well, it turns out people take you up on that offer. And so this is a project on an incredibly tight site in Beverly on an existing campus. It was an old residential cul-de-sac actually that got turned into a campus over time. And they have this very challenging site between a lot of conservation overlays that also has this radical topographical change within the depth of the building of 11 feet that is currently mitigated on the campus by a long circuitous outdoor pathway. It wasn't accessible. So the building had this challenge of becoming this active bridge between upper and lower campus, but then also we are 100% committed to being a certified Passive House. Like, okay, well, we've had this challenge before, let's try it again. And then added to that was this communal aspect to the school, and they actually polled the entire student population. This is grades 6 through 12 of what they wanted in the space. And this crazy thing that came out of it was this idea of adventure, that they want this, they have this forested campus, they want it to be this adventurous building, which added another layer of complexity to a Passive House approach. The gut reaction as a Passive House would be to say, okay, we want to make a bar building because it's as compact as can be. It has as small a volume as possible to surface area, which is, for us in COTE, that makes sense. That's going to be an achievable Passive House. But then it just has this kind of cobbled on bridge to get to upper campus as part of that necessity. And we're like, that's not really doing much for us programmatically. It's not doing much for us as architects, as designers. Well, what if we thought about the program actually becoming that accessible bridge to the upper campus and the building becoming the armature for that accessibility? And that was a great solution that everybody loved. But what we didn't know at that point was, could we certify that? And we kind of said, okay, well, we'll accept that challenge. We did allow it to shift and manipulate to try to access that grade specifically, and then become this kind of bridge from that entry court up to that upper campus as this kind of wedge structure. All of these decisions made with kind of this confidence behind us to say, well, I hope we can kind of pull off that energy ask in the end. And then just a cross section through that same bridge structure, looking up through the program spaces into that upper campus from the design phase. It also involved several communal spaces for the entire school population when it's within its building. So not only does it have this complex form, but it's also a high occupancy building, which those of us who are familiar with some Passive House work might know becomes a particular challenge for Passive House in the area of overheating. So again, stacking up the challenges and trying to march forward with a building that can be transformational and still achieve a high sustainability goal. We knew that we had some things to help us in that. We had the ability to kind of locate those high occupancy spaces on the north side of the building to try to make sure that we're not overheating spaces that are exposed to solar gain. And when we were starting to look at the early energy models in PHPP, we were starting to get that kind of feedback loop that we know is going to potentially be a successful Passive House, where we're getting close to a 1/3, 1/3, 1/3 breakdown of heat production between the sun, the people in the building, and the mechanical heating system itself. So it was looking like it's definitely possible. And so we continued forward with that. And we were able to utilize that form, that bridge that connected to the upper campus, as a circulation armature that actually we could lock into a little bit of solar gain there. And typically on some of our higher occupancy buildings that we have gone to Passive House with or certified, gone all the way to certification, that's always been the kind of push and pull, is how much solar gain can you actually use? It flips the script on a residential home, as those of you who are familiar with Passive House might know, that we've got to be really sensitive to those overheating conditions, but being able to use this armature of the hallways that are not highly populated as a way to heat the building passively ended up becoming actually a successful solution, because it kind of created this knuckle, and all the program spaces could sit on the outside of that. And we were still able to achieve, the things that they really needed out of the space, which is this great all-school meeting, by situating it to the north. The north also happened to be the entry approach, so it could become that beacon that the school was hoping for in their first building project in 16 years. It was a very important building, very present building on the street and approach to the school. Just another rendering from the upper campus, where that 2-story bridge allows it to kind of feel lower in the landscape and not take over the upper campus where their other academic buildings are. And then just some shots. This is from actually 2 weeks ago on site, some aerial drones, and you can see that canted volume that reaches out becomes the bridge to the upper campus and meets as a 1-story building with their other academic buildings up on that hill. And then extends out to become that facing facade to the street. And then another drone view looking down at that facade. Again, still in construction. We had a couple weeks left, as I mentioned, but is on track to be passed out certified. Their final blower door is actually tomorrow. Luckily, they've done a preliminary one, which passed. So we're knocking on wood still until tomorrow evening, but it's looking like we are going to be certifying this building, which is super exciting. And not only that, but we're able to pull it off at their budget, which is maybe the last challenge that I didn't speak of at the beginning, but probably the most difficult one. This building, independent of site costs, came in at $275 a square foot and will be passive house certified. So again, it's about trying to lean into that experience and that initial dedication to passive house as a way to try to take on new typologies, new challenges, and push that potential for buildings to improve climate forward. This building really focused on passive house as its key goal criteria for sustainability. So it wasn't looking at an overall building materials objective. But the next project we're going to share is one that is even larger in scale. So this project's about 13,000 square feet. The next project that we're going to look at is for College Atlantic, which is also finishing up. They're actually occupying this building in 2 weeks. So the building is turned over. We have a C of O. And this is a project where they wanted to take that all-wood approach all the way throughout the building and become kind of this kind of real beacon for what high performance building could be at scale. So College Atlantic, for those of you who aren't familiar, is a campus, a very, very tiny campus that took over some old carriage houses from, old summer homes from the early 1900s on the coast of Frenchman's Bay in Bar Harbor, Maine. It actually has direct access to Acadia National Park from its campus, which is very unique, probably the only campus in the US that could claim that, and also be something that they pride themselves on, the greenest campus in the US for 4 years running. So it's a pretty high bar. They came to us, we're in collaboration with Susan T. Rodriguez out of New York City on this project. And they came to us specifically because they needed to align with somebody that was able to align with their mission on sustainability. This is a campus that came with a sustainable action plan that was 9 sections and about 20 pages long, which is the most specific action plan I've seen from any institution. But this is the first building they would have ever, that had ever been taken forward to implementation under that action plan. And it was really important to me because I grew up about 30 minutes from that campus. This is actually me on the top of Cadillac Mountain as a 4-year-old. And so with my mom and my sister. And so you can actually see, not in this picture because my head's in the way, but you can see their campus from the top of Cadillac Mountain, which for those who don't know is the point in the US where you can first see the sunrise every day. and it's part of Acadia National Park. And it was a super exciting challenge for me to be involved with this project just because of that personal connection. And as I said, they came to us with this criteria for performance goals and objectives, is what they called it, across 9 categories. And we set up this matrix right early on, because hitting all of them required a lot of management. It wasn't just an energy project. It wasn't just a LEED project, just a passive house project. But they wanted no certifications, but hit all of these metrics. And that was their standard. Luckily, we were able to pare a few down because they didn't directly apply to our project, but not many. And we were excited to actually engage with almost all of them, except for the ones that didn't actually have a direct relationship to the project, this specific project. Starting with energy, which made up the most areas of performance within their matrix. It was quite clear from the initial go and the design that they derived many of these parameters out of Passive House. So it was a really good alignment with our firm. And so we could really get into it right away with the energy component. And you can see, oh, sorry, I want to go one back. Actually, we'll just plow ahead. So with experience in other academic projects and other large buildings at the time, we were able to think about a synthesis for this building as to how we would approach a Passive House solution. So as you may have seen from our presentation, we like to come up with these monikers for the different projects we've done. And we had the Alnoba project in Kensington, New Hampshire, which had recently been completed. And we called that one Everything Passive House, because it was a building that had all these crazy different spaces: commercial kitchen, active wood burning fireplace. And that was one we were thinking, is there any possibility to certify this? And that's why we call it Everything Can Be a Passive House, Everything Passive House. And this tiny school in Belfast that we've done recently as well, which was on maybe the lowest budget we've ever done for Passive House. And we're like, okay, well, if we can do academic building and we can do this really complicated thing with all these different programs, what if we were to synthesize them together and think about a building that's twice the scale of Alnoba, but with programs similar to a school? And that became kind of the mantra around this project. And we got into it right away with energy modeling. This is another quote we like in the office: the more you know, the less you need. And because we're early adopters of Passive House, we energy model internally all of our buildings. We require all our staff to know how to run an energy model. And so knowing all that from experience allows us to make initial decisions right away and not have to wait for that testing to catch up with the design. And it put us in position for success on this project specifically. But there's these 2 key areas of the building. This is our first academic, purely academic building that we'd done. And it has not only a full higher education chemistry lab in it, which is up here in kind of the corner of the building, but also, and this is unique to College of the Atlantic, it has a zoology lab where they dissect mammal carcasses, sea mammal carcasses from all over the coast of Maine. So allied whales will bring them a whale that they've found, a beached whale or a beached seal, and they'll do dissections in this space. And so doing dissections of a dead mammal requires 12 air changes an hour during dissection. The chemistry lab requires 6 air changes an hour during active experiments. And we'd never approached a Passive House solution with that much air having to be moved. But we got into it right away and learned quite quickly that ventilation component was going to be 40% of our losses. And so we custom designed with our mechanical engineer, a direct outdoor air system, ERV, that is literally 30 feet long and 10 by 10 square, with a 9-foot diameter enthalpy wheel that allowed it to move slowly enough that we could recover enough energy from that zoology lab at max capacity of air changes to still get that energy level below the threshold needed to achieve the energy conservation levels necessary for Passive House. Also, daylighting and active daylight harvesting became a key component to reducing EUI on this building. It also happened to be a parameter within their matrix, which was the first time we'd seen a college actually put a line in the sand about daylight control, automatic daylight control. Usually if you have a lead project, you might engage with that, but it's not often a directive from the client, which was unique to this project. And what that meant in the end was that we got really, really close to their EUI goal just through the design parameters. We were at 25 kBTU per square foot per year. Their threshold in their matrix was 24, but that was before we added in the renewables, which was also directive. And luckily, just in their site, sorry, what's going on here? Oh, sorry. With the added renewables, we were able to bring that EUI down to 11 kBTU per square foot per year, which outpaced not only the targets for AIA 2030 at the time, but also the targets still 4 years in the future from now. And when I talk to firms about, signing up for the AIA 2030 challenge, or what they would need to do, what first steps could you take to try to start thinking about reporting on DDX and achieving those goals? I always say, look at your biggest building and try to make that as good as possible, because that's going to be the thing that's going to be the rising tide that raises all ships in your office as far as averages. And you do have a lot that you can do with these larger buildings. And this was, I think, a good example of that, leaning into that kind of baseline approach of Passive House. The other big thing that we started to learn is that activating spaces allowed us to actually reduce EUI in a lot of cases. They had a lot of old buildings where students just wouldn't hang out in them because they weren't designed as public spaces for congregation. And just increasing their occupancy expectation actually helped increase the passive heat gains in the building and reduce their EUI. And this was something that they kind of blew their mind a little bit, because they had all these old dark spaces and the kids didn't want to be in them, but create a nice bright space that's active, and all of a sudden that full-time equivalent allows us to inch the EUI down a little bit. And so then thinking about ecological habitat, incredibly important to them, close to the park, close to Acadia National Park. We did make this project a case study for bird-safe glass as well. So one thing that's another great overlay with some of the earlier work we did in Passive House was we're very experienced with importing, as Matt had described in detail, products from Europe. And we learned quite quickly that Ornolux glazing, which I think a lot of us are familiar with, is expensive here in the US, but as originally a German product, the window manufacturers that were using anyway for a Passive House approach to the building offered that as an option for the glass. And we didn't even know that until we asked the question. And we're using Ornolux throughout this building. And now that the glass is installed and the building's nearly finished, or nearly occupied, to say it is finished, it's a really amazing product where it really is truly optically clear from the interior to the human eye, unless looking at a very oblique angle. And so far, so good. We haven't had any bird strikes yet. We'll see how it goes. But we have signed on with Maine AIA COTE, who's made a dedication to habitat and bird safety in our state as a case study project. So we'll be monitoring this project over time and trying to record if we see any instances of that happening. Another, of course, though, key component is the sustainable resource stream and materials. And so this is where this building, as Matt said, became a real test case for how you could take the concept of carbon sequestration to scale in a larger building, and how far can you go with it. So when we think about resources, I think as architects, we might think technically about it, but there was a time in our state especially where, this is what we meant by resources. We meant the log flow down a river in northern Maine, and this was our natural resource, our natural renewable resource. And I don't think anybody would be thinking about it that way, but it was what we were building everything with. It's what we're making into paper. And there was an interest at the college of going beyond what 10 years ago we might have thought about as sustainable material specification, which would just be local and natural materials, and thinking from a data-driven perspective about what that meant. So really, it's about all those computations and calculations that Matt presented about sequestration and taking it to scale, and not necessarily just thinking about them as surface finishes. So this building, does what Matt described. It's not just using the resource shown below of the wood chips for wood fiber, which is cool because this is it's a 30,000 square foot building, all wood fiber insulation. That's a really exciting thing, but also then taking and looking at how can we use mass timber, sourced sustainably locally, and make that a structural system for a larger building. So a building that would normally be thought of as steel and concrete, that would be the gut reaction for the structural engineer. This is how we should design this building, but trying to think about a similar structural system in wood. We kind of leaned into that and went for it. And so we're talking about an all wood assembly here, wood framed point-loaded structure. So it's a mass timber building, but not CLT, so glue-lam beams, wood infill walls, wood installation, wood fiber insulation, as Matt described in his section of the presentation. So that carries through all the way. Interior finishes, there's some non-wood interior finishes, but we have lots of wood interior finishes as well, all wood exterior siding, and of course the wood structure and wood insulation. Here's some pictures from earlier in the construction, and these glulam beams are doing 30-foot spans. These were milled in Quebec, or milled and fabricated in Quebec, sorry. And then a solid spruce structural deck on top of that. So that's a 2-inch thick solid spruce deck with the glulam beams. And even the spaces where the glulam beams end up being concealed, we're trying to reflect that in the ceiling finishes as well, the wall finishes in places that bringing that wood, the locally sourced, this is Eastern white pine, into the building. This building has a very industrial character in the way it is finished out. So a lot of exposed utilities, but that was largely to try to show off that assembly as much as possible and make sure that there was a didactic relationship with the building itself and the students that are eventually getting educated in the building. Just some images of the exterior. This is a corner of the building and all Eastern white cedar siding as well, so locally sourced siding. Some images within the building. This is the central corridor, or the kind of armature that wraps around the interior space framed by the building, which everyone congregates through to the classrooms, and these bridge connections to the upper corridor to office spaces on the outside, which you can see through this door. And we took that into Tally. We use Tally for our life cycle analysis through Revit. It's an awesome tool. We have learned, because we tend to be tire kickers in our office, that it's really only as good as the data sets, but that's a question for another talk about how to do LCA and how that works. But we started to analyze quite early structure independent of the rest of the building, what would happen, and from a life cycle and embodied carbon standpoint, global warming potential standpoint, if we were to compare it to a steel and concrete building. And what we learned quite quickly, it's very similar, to the math that Matt had showed on a very, very small project. So that's about 1,300 square feet, 1,400 square feet, Matt, something like that. This is 30,000 square feet. That, the math scales pretty easily, and that we can get this big negative carbon situation, negative global warming potential from sequestering so much carbon in wood. Wood's 50% carbon by mass on average, depends on the species. So you can do a lot by all that carbon that gets soaked up in that tree when it's alive. It's our single greatest renewable resource, we feel as architects, and leaning into it at scale really starts to move the needle a lot. And when we take that to the entire project, we were able to show the client this, these numbers are very exciting to them, that we were saving over 5 million kilograms of CO2 equivalent over 50 years when we combined operational energy reduction through Passive House to all that carbon sequestration in the structure, which was the equivalent of of driving a Prius for 2,400 years, driving their night bus, which takes kids around to their rental houses outside of the campus in Bar Harbor for 355 years. They could drive that for that long with the amount of carbon they're saving in this building. And then it was fun because the president of the college has this 1989 Toyota Land Cruiser, and we calculated that he could drive that for 544 years for the same amount of carbon that we're saving in this building. But the really kind of one that moved me was that the entire COA, College of the Atlantic community, could give up driving completely for five and a half years, and that would have the equivalent impact of just building this building. And so we make all these choices as consumers to, do the best thing for climate, but oftentimes as a collective, as a social group, we can make a much, much more significant impact by just building a really great building that helps reduce global warming potential. So just to finish with some nice images, this is from their corner flex space. I mean, who doesn't want to go to class and look out onto the Atlantic Ocean? Very rare opportunity, really beautiful, beautiful site. And just some a corner detail and a furnished corner of the upper hallway. A communal stair at the south entry to the building. Here we have German all wood curtain wall. Not all wood, it's aluminum pressure cap, but wood curtain wall with Ornolux glass, wrapping stair. This is from the exterior, looking into the main entry of the building again, where this is just at the finish of construction. This is a few weeks ago. Just some images of the detailing. We got that same south stair from the outside on the right. Some images of the German curtain wall on the left. And from the air, because it's always nice to see these projects from above. And this is Frenchman's Bay behind the project. And this kind of frames this open area and hugs the edge before a 70-foot drop drops off to the Atlantic Ocean just to the east. You can see here. And this project represents, this is our entire catalog of projects from our DDX, from our AIA 2030 DDX entered in. College of the Atlantic is right here. And again, as I like to say in these talks, like trying to leverage those big projects is really a key as architects, because if we think about the scope of what we affect with our decisions, that ratio of square footage is really key. And if we can do well by our big projects, do well by our big clients, then we can do a lot. We have this great opportunity to affect change positively through the buildings we design. And this is just, we always try to keep this graph updated because it's nice to look back at and see how we're doing. And the final EUI, again, 10.62. Buildings of this type on national average are usually over 100 kBtu per square foot per year. And it's pretty nice to be able to see the building that can do all this, high level academics inside with high needs, high energy spaces, and offset its energy just on its own roof, because that's only possible with the passive house plus this approach to sequestration. It really does come full circle when all those are tied together. And so we really thank you for your time. I'm sure there's questions, and just leave us with this view. We can see Cadillac Mountain in the back here. And this is the viewed from the Atlantic Ocean Center for Human Ecology.
Michael, you're muted.
Michael, you're on mute. We'd be pleased to answer questions, but I think we're dealing with some technical difficulties here. Blame it on Zoom. That's what we can all do this year, right? Blame everything on Zoom.
All right, well, I'll take it from there then. And everyone's welcome to jump in, either put a question in the chat, or you can unmute yourself and jump in as well. So thank you, Matt and Timothy. There's a question in the chat. I did not ask this, but I'm an engineer and I'm interested. If you could describe the mechanical systems that you used for these projects. I know you described the energy recovery ventilation system 2 projects ago, but if you could speak just high level for what you used on these projects.
Well, it's definitely different depending on the project, like the project that Matt presented versus the larger buildings. I'll maybe start with one of the bigger buildings because they both have very similar systems, and then I'll turn it over to Matt to talk about the project on Lake Warmog. So these buildings are actually both the Waring School and College of Atlantic are centralized VRF systems for heating and cooling, and a centralized energy recovery ventilator direct outdoor air system unit. Different models on each one. So this building, because of the complexity of the different programs, is a custom unit that we had designed and built specific for this project, whereas the one at the Waring School is a Ventacity unit because it was important that it be Passive House certified in order to get the certification. Since College of Atlantic has no interest in certifications, we could customize and not have to worry about the process of testing for certification. Both of them, their sensible efficiency is close to 90%. So that's key, certainly, for keeping, when we're bringing in out fresh air, and this is obviously everybody knows about this after the year of the pandemic, but we've, as Passive House designers, are bringing in 100% outdoor air always, for all of our projects. And so to hear people finally come around to that is kind of like, oh yeah, you should be doing that the whole time. It's really important to have that high efficiency so you're not blowing cold air into space that has to be reheated. And those units, I think, on a high occupancy building do the lion's share of the work. Both these buildings also have DX loops split off the VRF system to pre-cool the ventilation air, which is really about humidity control. That's why we have them in both buildings. And they both use the same VRF system, which is an LG system.
Okay.
I don't know, Matt, if you want to talk about the other project.
Just briefly on the small project, small scale residential, we're using a Zender 330 for ventilation, so 92% recovery ERV. Obviously, Passive House proposes that internal gains of the majority of the heating system, as Tim showed in his graph. So we always really start with that approach. It had the large glazed area was facing north towards the lake. So we didn't have so much of an issue with overheating with that glass, but we had a reasonable space heating demand. For that, we used a air source heat pump with a air to water heat exchanger, and we had a radiant floor and a forced air mechanical system central ducted throughout the building, which included the ventilation airstream. Given the scale of the project being quite small, we didn't run the risk of not being able to sufficiently distribute the fresh air with that approach. And I think the air to water heat exchanger was a space pack. I forget who makes it, maybe Fujitsu or somebody like that. But I guess in many cases, if we don't have an air conditioning requirement, we'll do straight electric, which seems old fashioned, but when your heat demand is 2000 watts for peak, that doesn't really, run afoul of a high performance concept. But otherwise, when there's air conditioning required, then we'd certainly use air source heat pump for both. And, that tends to work pretty well.
Thank you. And if I am to take on any common threads there, dedicated outside air ventilation systems, heat pumps as your primary sources of heating and cooling, electrified to no fossil fuel use, but using the heat pump because it's a much more efficient way when possible. But it's actually interesting, Matt, that last point you made, that electric resistance, even though it's not that efficient, when you make the building so efficient, it actually could be okay. So I think we might have Michael back.
I'm back, especially
Great.
with PV with photovoltaics on the roof. It's pretty efficient. So yeah, I wanted to say that was such a great presentation. Someone said it in the chat, and I wanted to say it also. Thank you. Beautiful graphics, beautiful work, and a lot of good data about your work, which is always appreciated. Did we hit the question about fire codes? Someone asked whether you had any trouble with fire codes regarding the finishes as you are working on these larger buildings.
Yeah, so we're definitely trying to learn how to thread the needle on what scale you can get to based around allowable area and construction type. There will be some advantages coming in IBC 2021, as I think probably a lot of people know, with mass timber that will allow for more square footage to be built, because the testing does show, and Matt can talk about this as well, that there's not a lot of risk really in structural failure from mass timber structure. So the College of the Atlantic building probably represents close to the upper end of total square footage that you could, well, that's not true. We could get a little higher, maybe about 50,000 square feet in that class of building. It's a different calculus, of course, when you get to things like multifamily and things like that, as we all know, based on allowable area. But it's an advocacy piece too, which we encourage people to be active in, at the state level even, to try to make sure that the codes are responsive to the actual testing and not arbitrary understanding of what burns and what doesn't, because it's just not really true. and Matt should talk about that more, especially with the wood fiber. Both of these buildings, the Waring School and the Center for Human Ecology for College of the Atlantic, are within that allowable threshold for that construction type. So we didn't have much of an issue, and we just try to be within the guidelines for finishes, exposed finishes. One thing that we did learn a lot about throughout this process is just that unfinished wood actually is less of a flame spread threat, even in the data that's used in IBC, than treated wood. So leaning into unfinished materials can help you there if you want to expose more from an interior flame spread issue. But as far as, fireproofing and construction type category, both of these were within, and as of right, we didn't have to get any variances for them. But Matt, maybe you want to talk a little bit about some of that testing, because I know you guys have been working on that a lot at GoLab.
Yeah, so I think to Tim's point, I think it sometimes goes counter to what we'd expect with wood and how it performs. These mass items, they form a char surface which protects the structural integrity of those systems, which I think is, yes, it burns, but it burns to a certain extent, and then it can't burn any further at any great speed. So that's really how that protection works and functions. In the wood fiber case, one would also think that would burn, but again, it has a sort of density to it, which when you take a blowtorch to it, it will flame up, but it extinguishes itself just because of the mass of that. And when you compare it to other like foams or fiberglass, it really performed extremely well. And we have some great videos, unfortunately not available, to demonstrate that. But I do think, again, people, when they think of building materials out of wood, they think they're going to burn, they're going to rot, bugs are going to eat them, and water's going to damage them. Couldn't be further from the truth. I mean, wood is developed in nature to manage moisture, insects, and other things, and those properties, when appropriately processed into materials, also function really well. As I said, like the wood fiber insulation, the board acts just like Gore-Tex. When you put water on it, it just rolls right off it. It's hydrophobic. It doesn't trap it at all. And so I think there's a lot of preconceptions about what wood is and does, and what the liabilities are, that I think, to Tim's point, it's really about looking at the data and actually how it performs. And I think for us, when we're introducing wood fiber in the North American market, it's about education around those items and and the benefits, and to really point out the liabilities, which in most cases aren't really real at all. So again, I think for us, wood is the old new material. We've been using it forever, and I don't think we've really tapped what its potential is and how it can really address climate change as a building solution.
Great, thank you. There's also a comment in the chat about, will the slides be available? I wanted to let everyone know who might not have been on the call at the very beginning that tonight's presentation is being recorded, and the BSA will post it to the Committee on the Environment website within the next few weeks. Matt and Tim, do you have any consultants who you work with who you'd like to sort of give a shout out to? Or do you find that you've developed a network of colleagues who are really good, who you appreciate, or are you having to carry a lot of the weight yourselves? Maybe a little of both?
Tim, want to go first?
No, you start.
I definitely think when you get to, let's say from the beginning, starting at single family passive house, there certainly was a lot of the latter, Michael, of trying to do a lot of education to consultants, and that still is part of the job at Opal, because oftentimes we're pushing things maybe beyond what consultants might be used to or comfortable with yet. But I definitely think when we get to this type of scale, there's a value that the consultants bring that we just cannot. We have these goals, we have these things that we know are possible from the data that we're reviewing in the office and the design approaches we want to take. But we really do need them to help us, certainly in some of these more complex projects. We have a great working relationship, for instance, with Thornton Tomassetti's office in Portland for structural engineering. And it's a long-term relationship with Paul Becker, who's been an early advocate for mass timber in Maine and in the region, which has really been fruitful for us. So we work with them a lot. We've had some good relationships on the two projects that we've shown you with Van Zelm, which is an engineering firm out of Connecticut, that really is kind of thinking forward on mechanical engineering and how it can apply to truly high performance solutions. And then they were definitely integral in coming up with the systems for both the Waring School and College Atlantic. Yeah, I mean, and I would also just say that, this project, College Atlantic, that you're seeing on the screen now, was a design collaboration as well. So, we're working with Susan Rodriguez out of New York on this, in a collaboration together to try to bring this to fruition. So it's, I do think some of these projects really aren't possible without that team that's totally dedicated. But to get to this point, 10, 12 years down the line, has taken a lot of education to all of those folks along the way with what we want to try to do. And, there's footsteps there too, for sure. So I don't know, Matt, if you want to give any shout outs as well.
Yeah, no, I think it's a great question. And, because it's always so important to have a great team around executing buildings. I think particularly on the performance side, we've always been, as you've gleaned, very data driven. And I think that has been something, we've done our own internal energy modeling. We have our own experience, a lot of testing, field testing data that we've used. And I think as we've worked with different consultants, we always like to refer back to the data and what that's saying, and sort of have a very a sort of aligned approach to what should be happening in the buildings and how we should design around that to ensure that the passive house principles and concepts really manifest in the final project. And I think since we had a long, started with the first passive house in Maine, the 12 in the US, we have a lot of experience. And part of that was sharing and working together collaboratively as we change scales to build different building typologies, and we're leaning on consultants, but also to kind of refer back to what the original passive house concepts were and making sure that systems were designed in line with that. I think the other thing that we've always asked both our staff internally and ourselves and our consultants is we seek to innovate, and we need people who work with us to collaborate to innovate as well. There's a lot of risk averse professionals, and I totally understand why one would be in this profession. but we oftentimes ask a lot more and don't allow that to hold us back. And so, as Tim said, with Paul Becker at Thornton Tomasetti, he's just been a fabulous collaborator with us, particularly on very tricky, unusual structural systems, and continues to do so because we're getting into prefabricated CLT composite wall panels, so full CLT wood fiber window installed large scale pre-cut panel systems that we're installing, which are very heavy, very big, with a lot of unique kind of structural connections that are required. And without a great structural collaborator, you can't take those kind of projects on. So we're really thankful for the people who go out on a limb with us, because we think innovation requires a certain amount of risk taking, careful, obviously calculated, but it takes getting out of your comfort zone. And so finding professionals who kind of will go down that road with us is always so important.
That's great. Thank you. Yeah, I've worked with Dave Madigan and Tom Madigan from Van Zelm, who Tim mentioned, very strong. I believe they worked on the Cambridge School of Weston, which is a project that Architects, who I worked with previously, constructed. And in some ways, the site conditions reminded me of the grade change that you dealt with. They dealt with it in their science building for the Cambridge School of Weston, science and art building. Although they dealt with it differently. That's a timber glue lamp timber frame building. It's quite interesting.
Nice.
Let's see. I'm going to open the floor up. I don't see any other questions in the chat, but if anyone wants to unmute and jump in, or I think everyone has the ability to unmute, and if you don't, you can raise your hand. And I see some people are logging off the call. So I think we're winding down. I don't know if Patrick, Matt, or Tim, if you have any final words, but I think we'll give it sort of one more comment and we'll sign off.
Thanks everyone for joining us today. We're always happy to talk about what we're doing. We'll be happy for any follow-up data or information about what we presented here today. We're certainly interested in sharing information and not hoarding it. And so, again, we're happy to have a conversation. And if you're up the main way, please stop by. Socially distanced, of course. Happy to visit.
Yeah. Thanks, everybody.
Okay. Well, I want to say loud and clear on behalf of the BSA Committee on the Environment, thank you to Opal Architects. Fantastic presentation. Really exciting. Thanks for your generosity. All right, that's it for us. Good night.
Thanks.
All right, thank you.